the dynamics of power systems operate across various timescales. The timescale associated with the controls of converter interface generation CIG technologies spans from microseconds to milliseconds, encompassing wave and electromagnetic effects. With the increasing adoption of CIGs, faster dynamics are becoming crucial for analyzing the behavior of future power systems, surpassing slower phenomena that occur over milliseconds to minutes. Traditionally, focusing on the timescales of electromechanical transients allowed for significant simplifications in power system modeling and analysis. One major simplification was the assumption that voltage and current waveforms were primarily dominated by the system's fundamental frequency 50 or 60 Hz. This led to the development of quasi-static phasor models, which relied on steady-state voltage and current representations. However, this approach primarily addressed slower dynamics while overlooking high-frequency dynamics, such as those stemming from the switching of power electronic devices. Below is the list of 5 power system stability categories along with a brief explanation for each. Frequency stability focuses on the system's ability to maintain steady frequency levels when there is an imbalance between generation and load. Rapid deviations or prolonged frequency excursions can trigger protective relays and lead to broader outages. Voltage stability involves maintaining acceptable voltage levels throughout the grid. It ensures that the system can accommodate variations in reactive power demand without causing a voltage collapse. Rotor angle stability concerns the maintenance of synchronism between synchronous generators. It reflects the ability of rotating machines to maintain a stable inter-machine angle during and after disturbances, which is essential for coherent system operation. Inverter-based stability pertains to the dynamic performance of systems with significant converter-interfaced inverter-based renewable energy sources. This category addresses challenges such as fast control responses, reduced inertia, and interactions between inverters and the grid. Resonance stability deals with the prevention of resonant oscillations that can arise from interactions between grid components. These oscillations, if left unchecked, can amplify disturbances and potentially lead to equipment damage or system-wide instability. These categories offer a comprehensive framework to evaluate and manage modern power systems, especially in an era marked by diverse energy sources and advanced control technologies. Considering the operational timescales of CIGs, it is essential to extend the scope of analysis to include faster electromagnetic dynamics when these significantly affect overall system behavior. This approach focuses on 2 primary timescales, electromagnetic and electromechanical. Electromechanical phenomena are further divided into short-term and long-term dynamics, which are commonly analyzed using phasor-based approximations. However, such models are not suitable for representing electromagnetic phenomena, which require different analytical methods. This discussion emphasizes the classification and definition of power system stability phenomena, factoring in the increasing role of CIGs in bulk power systems. The classification is based on the intrinsic dynamics and components involved in stability challenges. Timescales help identify the relevant components, phenomena, and controls that must be modeled to accurately capture specific stability issues. In this context, the discussion excludes certain aspects, such as local instabilities due to incorrect control settings, control loop instabilities that can be analyzed without modeling the entire power system, stability issues specific to microgrids, and electromechanical or electromagnetic wave propagation phenomena. Characteristics of converter interface generation. CIG technologies, the growing presence of converter interface generation in the energy mix has introduced new challenges in power system stability. These arise due to the distinct dynamic behavior of CIGs compared to traditional synchronous generators. Key factors include the interaction of CIG controls, reduced overall system inertia, and limited ability of CIGs to contribute to short-circuit currents during faults. Key characteristics of CIGs and their controllers. The performance of CIGs is largely governed by their control systems and the strategies employed to manage the power electronic converters that link energy sources to the power grid. Most large-scale CIGs are equipped with voltage source converters or similar designs, enabling full 4-quadrant control. This allows for independent management of active and reactive currents within the capacity of the electronic switches, providing precise and rapid control of power flow under most conditions. While CIGs pose challenges, they also offer exceptional flexibility in controlling energy sources. For example, technologies like photovoltaic PV systems and battery energy storage systems best enable rapid and sustained frequency responses. The key considerations when assessing the influence of CIGs on system dynamics include short-circuit current contribution. CIGs generally offer limited short-circuit current support, with contributions ranging from none in cases where converters block during severe faults to a maximum of about 1.5 times their rated current. Some systems, like Type 3 wind turbines with double-fed induction generators, can provide more short-circuit current since their stators are directly connected to the grid. Role of control loops. The phase-locked loop PLL and inner current control loops significantly affect dynamic recovery post-fault. For connection points with low short-circuit strength, these controls may exhibit oscillatory behavior due to synchronization issues or excessive controller gains. Adjusting these gains can help mitigate the issue, although the specific thresholds depend on the equipment and system setup. Dynamic performance determinants. The overall behavior of CIGs is shaped by the dynamic characteristics of the PLL, inner current control loops, and higher-level control strategies. These dynamics span a broad range, from high-frequency electromagnetic phenomena kHz range to slower voltage and frequency stability issues Hz range. Definition of power system stability. The definition of power system stability aims to provide a clear, practical framework for understanding and applying stability concepts in power systems. It offers a physically grounded perspective that aligns with system theory while remaining accessible to engineering practitioners. Despite the transformation in power systems driven by the integration of converter interface generation CIG and power electronics-based control devices, this definition continues to hold relevance and remains unchanged. Formal definition. Power system stability refers to the ability of an electric power system, under given initial conditions, to return to a balanced operating state after experiencing a disturbance. It requires that most system variables remain within acceptable bounds to ensure the system's overall integrity and functionality. The concept applies universally to the dynamic behavior of interconnected power systems, encompassing both synchronous machines and conventional components. Particularly, it is effective in describing stability performance in systems with CIGs. Similar to how a remote synchronous machine losing synchronism does not necessarily destabilize the entire system, the dynamic response of an isolated CIG also has limited impact on system-wide stability as long as it does not trigger cascading failures. To understand this stability in detail, mathematical models of power systems based on differential algebraic equations are employed, along with definitions from system theory. With the growing use of power electronic inverters and the necessity to model protection systems, the principles of stability also extend to hybrid systems that combine continuous dynamics with discrete events. Stability in hybrid systems involve interactions between continuous processes and discrete events. Their stability depends on maintaining proximity to equilibrium points or converging back to equilibrium after disturbances. Lyapunov stability principles apply to these systems but require additional conditions ensuring non-increasing behavior during discrete events. Challenges in hybrid systems include phenomena like deadlock or infinite switching loops, conditions that arise due to model artifacts rather than real-world occurrences. Accurate modeling is critical to avoid these complications, especially in scenarios involving interactions between continuous and discrete elements. Real-world examples have highlighted the role of hybrid dynamics in power system events, such as voltage oscillations caused by transformer tapping and capacitor switching. These dynamics underline the importance of careful system design to manage the interplay between continuous controls and discrete actions effectively. Classification of power system stability and importance of classification. The classification of power system stability has evolved to include new categories, reflecting the growing adoption of converter interface generation CIG technologies. Two additional stability classes, referred to as converter-driven stability and resonance stability, have been introduced to address challenges specific to CIGs. These additions were necessary due to the unique dynamic behaviors associated with modern power electronic systems. In earlier classifications, the category of subsynchronous resonance was excluded because it fell outside the timescale of interest. However, with the inclusion of power electronic dynamics, the scope of stability analysis has expanded to encompass electromagnetic transients, broadening the timescale under consideration. Dynamic phenomena and modeling approaches. The dynamic phenomena addressed in traditional classifications were typically modeled using simplified techniques, such as the phasor or quasi-sinusoidal approximation. This approach was suitable for analyzing slower dynamics but is often insufficient for converter-driven and resonance stability classes. Exceptions can occur in cases of slow interactions within converter-driven stability, but such scenarios are limited. The inclusion of these new stability classes marks a shift towards capturing fast dynamic responses associated with advanced power electronic systems, highlighting the need for more comprehensive modeling techniques to accurately analyze these phenomena. Categories of stability: rotor angle stability, definition and phenomena description. Rotor angle stability refers to the ability of interconnected synchronous machines in a power system to maintain synchronism under normal conditions and to regain synchronism following small or large disturbances. Synchronism is maintained when the electromagnetic torque of a machine balances the mechanical torque delivered by its prime mover. Consequently, this type of stability depends on the machine's ability to preserve or restore this equilibrium. When there is insufficient or negative synchronizing torque, aperiodic or non-oscillatory transient instability may occur, involving significant rotor angle deviations. This is typically analyzed through numerical integration. On the other hand, the lack of negative damping torque leads to small disturbance oscillatory instability, characterized by oscillatory behaviors and unstable system eigenvalues following disturbances or topology changes. Categories of stability: rotor angle stability, impact of CIG integration. The integration of converter interface generation CIG does not alter the fundamental definition of rotor angle stability. However, as CIGs replace traditional synchronous generators, the overall system inertia decreases, affecting rotor angle stability in the system's electromechanical modes. This shift impacts the rotor angle stability of the remaining synchronous generators in several ways: changes in power flows along key transmission lines, potentially reducing damping of inter-area modes and transient stability margins. Replacement of large synchronous generators, influencing the mode shape, frequency, and damping of rotor oscillations. Effects on the damping torque of nearby synchronous generators, akin to how fax devices interact with damping, altering the stability of modes involving those generators. Categories of stability: rotor angle stability, replacement of synchronous generators equipped with critical power system stabilizers. Given these factors, there is potential to develop supplementary controls for CIGs to address power oscillations, similar to power oscillation dampers used in fax devices. Research has extensively analyzed the effects of CIGs on small disturbance stability. However, results can vary significantly based on the test systems and conditions used, making consensus difficult. The impact of increased CIG penetration on electromechanical modes and rotor angle stability can range from beneficial to detrimental, depending on factors such as the number and types of CIGs, applied control strategies, grid configuration and strength, and system operating conditions. Transient rotor angle stability: a reduction in total system inertia due to CIGs may lead to larger and faster rotor angle swings, increasing the risk of stability issues. Studies indicate that the impact of CIGs on transient rotor angle stability varies depending on factors such as grid design, CIG location, and control mechanisms. Additionally, disturbances and their proximity to CIGs or large power plants influence outcomes. The operation and fault ride-through capabilities of CIGs also play a significant role in shaping transient stability. Categories of stability: voltage stability, definition and phenomena description. Voltage stability refers to the ability of a power system to maintain consistent and stable voltage levels across all buses after experiencing a disturbance. This stability relies on the combined capability of generation and transmission systems to meet the power demands of connected loads. However, this capability is limited by the maximum power transfer to specific buses and the associated voltage drops caused by active or reactive power flowing through the inductive reactances of the transmission network. In cases of voltage instability, potential outcomes include loss of load in certain areas, tripping of transmission lines or other components due to protective systems, and cascading outages. Additionally, generator synchronization can be affected if the system operates under field current limitations. Categories of stability: voltage stability. A short-term voltage stability focuses on the dynamics of fast-acting components, such as induction motors, electronically controlled loads, HVDC links, and inverter-based generators. This stability typically operates within a timeframe of several seconds, similar to rotor angle stability and slow interaction converter-driven stability. Accurate modeling of loads and their dynamics is critical for analyzing short-term voltage stability, especially in scenarios involving short-circuit faults near loads. Categories of stability. Voltage stability. A common example of short-term voltage instability is the stalling of induction motors after a major disturbance. Motor stalling can occur due to either a loss of equilibrium between electromagnetic and mechanical torques or an inability to return to a stable equilibrium due to delayed fault clearing. During a fault, induction motors slow down as electromagnetic torque decreases, drawing higher currents and reactive power, which further depresses voltage levels. If the fault clears before the motor decelerates past a critical speed, the motor may recover and resume normal operation. Otherwise, it stalls and may either disconnect due to under-voltage protection or remain connected, drawing a large starting current until thermal protection disconnects it. In the latter case, prolonged voltage depression could lead to a cascade of similar issues for nearby motors. Instability driven by HVDC links. Voltage stability concerns with HVDC links. Voltage stability issues can arise at the terminals of HVDC links that use line-commutated converters (LCC). These issues are commonly associated with HVDC links connected to weak AC systems and may occur at either rectifier or inverter stations due to the unfavorable reactive power characteristics of the converters. This phenomenon is relatively fast, typically occurring within a time frame of 1 second or less. However, voltage instability can also result from the operation of transformer tap changer controls at the converter, which is a significantly slower process. The introduction of voltage source converters VSC and HVDC stations has greatly improved the stable operational limits of HVDC links in weak systems when compared to traditional LCC-based systems. Long-term voltage stability. Long-term voltage stability pertains to slower-acting devices such as tap-changing transformers, thermostatically controlled loads, and generator current limiters. It is typically characterized by a gradual reduction in voltage levels at certain buses in the network. Voltage transfer and support are further constrained when generators reach their field or armature current time overload limits. This type of stability generally requires long-term simulations, as the study period can extend over several minutes. It is often caused not by the initial fault itself but by subsequent outages of transmission or generation equipment following fault clearance. Long-term instability may result from a loss of equilibrium when load dynamics try to restore power consumption beyond the maximum power transfer limit. It can also occur if corrective actions are taken too late, preventing the system from stabilizing. Alternatively, disturbances like a sustained increase in load demand during the morning peak can lead to instability. Assessment of long-term voltage stability is typically assessed by estimating a stability margin, expressed as the increase in load power from an operating point to the maximum power transfer point, the onset of instability. This analysis considers the direction of system stress, load growth patterns, and generation participation. Linear and nonlinear analyses are often used together. Linear analysis helps evaluate the stability of an operating point using eigenvalues of the system matrix and provides insights into factors affecting stability. Nonlinear models account for additional complexities, such as limits, deadbands, discrete steps in tap changers, and time delays. It is crucial to consider both small and large disturbance conditions when assessing long-term voltage stability. Overvoltage instability risks. Although the progressive drop in bus voltage is the most common form of voltage instability, overvoltage instability can also occur. This issue arises due to capacitive behavior in the network, such as extra high voltage EHV or high voltage HV transmission lines operating below surge impedance loading, shunt capacitors, or filter banks at HVDC stations. Under-excitation limiters may also prevent generators or synchronous compensators from absorbing surplus reactive power. In such cases, the system may be unable to operate effectively below a minimum load consumption level, leading to instability. Frequency stability refers to the system's ability to maintain and restore frequency levels following disturbances. In power systems dominated by synchronous generators, frequency response during such events typically involves three distinct phases: the initial inertial response provided by synchronous generators, the primary frequency response, involving generators and load damping mechanisms, the automatic generation control, which adjusts the system to bring frequency back to its nominal value. Impact of CIG integration. Converter interface generation CIG technologies do not naturally provide an inertial response. Additionally, as these systems are often linked to renewable resources, managing reserves to enable primary frequency response can have economic implications, such as the spilling of renewable energy resources. Despite these challenges, studies show that CIGs can be highly effective in contributing to frequency response, especially battery energy storage systems. Unlike conventional systems reliant on mechanical components such as turbines or boilers, CIGs can provide faster primary frequency responses. Their electronics-based equipment allows for smaller droop settings and quicker reaction times, enabling larger and more effective contributions to frequency stabilization. Changing system behavior. As CIG penetration increases globally, the frequency behavior of large interconnected systems may resemble that of smaller systems, emphasizing the importance of refining controls for primary frequency response. Wind turbine generators, for instance, are capable of delivering an inertial-based fast frequency response, a feature offered by many manufacturers. Challenges from decreasing grid inertia. The displacement of synchronous generators reduces overall grid inertia, making frequency excursions faster and increasing the likelihood of instability. This underscores the need for efficient fast-acting controllers to mitigate frequency drops immediately after detection. However, reduced inertia does not always correlate with instability. For example, if synchronous generators remain connected but are partially unloaded, the system may retain inertia while gaining spinning reserves, positively impacting frequency response. Strategies like partial generator decommitment and redispatch have been recommended to balance these effects. Complexities of frequency stability with CIGs. The frequency response of systems with high CIG penetration is a multifaceted phenomenon that demands further exploration. Various factors including the proportion of CIGs, control strategies, system topology, and load patterns play critical roles in determining whether the presence of CIGs enhances or challenges frequency stability. Resonance stability. General overview. Resonance occurs when energy exchange takes place periodically in an oscillatory manner. If energy dissipation along the flow path is insufficient, these oscillations can grow, resulting in the magnification of voltage, current, or torque. When these magnitudes exceed specified thresholds, resonance instability is said to occur. Resonance stability encompasses subsynchronous resonance SSR, which can stem from either electromechanical or purely electrical phenomena. SSR manifests in two main forms: resonance between series compensation and the mechanical torsional frequencies of a turbine generator shaft. Resonance between series compensation and the electrical characteristics of the generator. The first type involves interactions between the series compensated electrical network and the mechanical torsional oscillations of the turbine generator shaft. The second, purely electrical resonance, is known as the induction generator effect IGE. Torsional resonance, torsional interactions between series compensated lines and a turbine generator's mechanical shaft are well documented, particularly for systems with conventional synchronous generation. Subsynchronous oscillations are generally classified into SSR and device-dependent subsynchronous oscillations DDSSO. SSR arises when significant energy exchange occurs between the network and the turbine generator at one or more of its natural subsynchronous torsional modes. These oscillations may be poorly damped, undamped, or even grow over time, posing risks to the turbine generator shaft's mechanical integrity. DDSSO, on the other hand, results from interactions between fast-acting control devices such as HVDC lines, static VAR compensators SVCs, static synchronous compensators STATCOMs, and power system stabilizers and the mechanical modes of nearby turbine generators. While such interactions are not always detrimental, they can sometimes enhance torsional damping. In fact, devices like SVCs are often employed to mitigate SSR by improving damping characteristics. Electrical resonance. In systems with traditional turbine generators, SSR primarily involves torsional resonance. However, with the advent of doubly fed induction generators TFIGs in variable speed systems, the induction generator effect IGE has emerged as a significant concern. IGE occurs when a series capacitor forms a resonance circuit with the inductive properties of the generator, resulting in subsynchronous frequencies where the circuit's apparent resistance becomes negative. This negative resistance is primarily caused by the inherent characteristics of the induction generator rotor and is further influenced by DFIG controls. When negative resistance exceeds positive resistance at resonant frequencies, self-excitation occurs. This leads to significant current and voltage oscillations, which can damage electrical components in both the generator and the transmission network. Mechanical damage, such as to turbine generator assemblies, may also occur due to large perturbations in electrical torque. The term subsynchronous control interaction SSCI is used to describe these events, as the dominant factor behind negative damping at resonant frequencies is the action of DFIG converter controls. While SSCI is closely associated with control interactions involving series capacitors, the core issue remains the electrical resonance between the series capacitor and the generator's effective reactance. Supplemental controllers added to DFIG converter systems can mitigate these effects and enhance stability.